I'm just going to do that. Just sit over there. And, joking, but I was a little bit. The station is going to be here, right? Huh? Yeah, I think so.
It will take like 60 seconds. That's what it's set. Yeah. 1, 2. Yes.
Okay,
Closer, so you can hear.
welcome everyone. Hello. So I'm Ilder and
I'm Harris.
we are co-chairs for HAID 2022 at Queen Mary in London. So thank you very much for coming. We'll start with a brief introduction. So you are on Mile campus of Queen Mary University of London. Hope you will enjoy London weather. We have tried to do our best to prepare an exciting HAID program. So Queen Mary is one of the oldest London universities. We are part of the School of Electrical Engineering and Computer Science. And we are welcoming HAID on campus here because we represent 2 centers interested in audio and haptics. Myself, I'm from Robotics and Haptics, physical human-robot interaction,
And I'm in the Center for Digital Music, one of the biggest research groups in the UK and in the world in audio computing, audio interaction, and audio perception.
great. So our workshop is supported by multiple organizations, including academic societies for haptics, audio engineering. Plus, we have also financial sponsors like Digital Environment Research Institute and Center for AI Music.
As I will tell you in a bit, we also got Springer to support us with proceedings this year. So a brief history of the workshop. It was founded in 2006 by Stephen Brewster, pretty active until 2013, every year in a lot of different places around the world. But then there was a hiatus. New haptics conferences have sprung out. The area now is much more different than it was in 2006. And there has been an effort since 2019 to revive the community. And that's what we tried to do with the 2022 edition. And in a bit, I will give you the numbers, the statistics. But I would like to call anybody interested in hosting the next HAID. Our suggestion is that to make this more sustainable, it will not have to be every year, but maybe every 2 years, probably in odd years when only the World Haptics Conference happens. So please, if you're interested in hosting this in your institution, come talk to us during breaks. We already have an interested institution, but we hope to get some more suggestions and ideas about this. Where do we stand right now? So the 2019 and 2020 editions were not as big as we had hoped. So this year around with Ilder, we put a lot of effort in bringing in support from the relevant scientific communities, from sponsors, from the industry and so on. Advertised a lot across both haptics and audio communities. So we ended up with 19 paper submissions, which is already twice the amount of submissions that we received in the previous 2 editions. We had a very rigorous 2-layer review process. This is our program committee, to which we are very thankful. And we accepted 13 papers that you're going to enjoy over the course of the next 1.5 days. We also had 9 demo submissions. We also introduced this idea of work in progress, inspired by the NIME conference. So, you know, more for younger researchers who maybe are not really into haptics or audio, but they're trying to get into the area, and their supervisor maybe is not part of that area, so they want some sort of support and so on. We also organized for workshops. Some of you attended some of them earlier this morning. And finally, we have 3 wonderful keynotes. Our participants are from quite all over the world, which is very, very nice. Approximately half from the UK, which is an important goal, and then the rest from as far as Korea and India and Japan. And our 3 keynotes, I'm sure you're already aware of them, is Andrew McPherson talking today at 5 p.m. in a different space. We'll take you there later. Charlotte Magnusson will be talking tomorrow morning here in this space. And finally, Sriram Subramanian, again in this space tomorrow afternoon. Very exciting, very diverse topics, because we think the HAID community needs to, to grow. It needs to also consider new areas of research. Very briefly, this is the program. So we are now in the middle of the first day, and following our opening remarks, there's going to be the first paper session, followed by the first keynote, our welcome reception and music concert prepared by the Augmented Instruments Laboratory here at Queen Mary. And tomorrow we have quite a full program, 3 paper sessions, 2 keynotes, and some nice rooftop reception at the end. And of course, our demos and work in progress posters during the lunch break tomorrow. So as you see, before going to that, we did try to bring together a lot of diverse elements and topics to try to push for HAID to continue. We also, the last 2 editions didn't have actually Springer proceedings, but they do have everything available online actually. So this year we approached Springer again, trying to restart the HAID proceedings as part of their LNCS series. And they were happy to support us. And actually they've provided us with free access until the end of September through this link. So if you try to access the proceedings through this link, you will have free access to all the papers until the end of the month, the next month. Finally, but very importantly, we want to thank our student volunteers from Queen Mary. They're the core of making sure that everything runs smoothly these days. You can see them around with this green tags, so any questions you might have, they're there to help you. Thank you very much. And yeah, that's it from us. Thank you very much. Welcome to London. Welcome to HAID 2022. And we are now ready to continue with our first paper session, which is about accessibility. And it will be chaired by Jeremy Marzon.
Also, it was mentioned we are broadcasting the talk through YouTube. So please, speakers, use the microphones here. Do not go away from the stage. Thank you very much.
Thank you, the organizer, to give me the opportunity to chair this session. I've been asked to be very strict on time, and you've been 2 minutes late. So can you please hurry? The first speaker will be Arthur Paté. He's going to talk about touch the music, displaying live music into vibration. I'll give you a sign about 2 minutes. So thanks for the introduction, Mr. Chairman. So Arthur Paté, I'm an associate professor in Lille, France, and this is going to be a short report about an EU funded project about transforming live music in real time into vibration, primarily for the deaf users. You will understand that it's in between a finished project and still an ongoing work for some reasons. So my hope is really to maybe to inspire some other projects, to get some inspiration from yours and contribute some discussion. Well. Okay. So a short background. We are obviously not the first ones to thought about transforming music to vibrations. A few examples, for example, this, I don't know if you see my pointer here, this MOD chair thing or the RS system. Such kind of solution proposes to fit objects or furniture with devices that vibrate according to the audio signals. Basically, they are passing the audio into a filter bank and driving several devices with, according to the energy, several frequency bands. We also can find this wearable haptics trend using very small actuators on garments that you can wear, for example, with the Vibrapixels here on the audio tactile gloves, but you might have heard about it this morning, for example. More on the commercial side, I don't know if you know these devices here. We've been working before with a subpack, for example. That's a backpack with two audio drivers on the back. And how these devices work is you take the audio signal in, you low-pass filter them, and you get the audio and the drivers. Well, just before explaining our objectives and aims and approach, I'm just discussing some issues that we found in already existing devices. I mean, issues that those devices won't work for our project. This is why we are especially targeting the deaf people, so we want them to experience music through vibrations. And there is no strong evidence that all these above mentioned projects really included the deaf users in the design process. So we're trying to fix that. The position of the exciters is not changeable by the users in those devices. And many of these devices use very limited transducer like ERM, eccentric rotating mass devices on which you cannot control the waveform or the frequency content, so you're very limited the vibrotactile message you can convey. And when they use more advanced transducers like audio drivers, like this, can I go back? Yeah. Like this subpack, they are limiting the signals to only to the low frequency content with two main issues. In the low frequency content is already, you can already feel it with your feet on the ground when you play music loud enough. And there is no indications about timbre or melody. You just have information about rhythm. Deaf people we worked with don't want this, they want to be able to understand timbre. So we have to find a way to render the higher frequency content of vibration, work with the deaf people primarily in a co-construction approach. And well, we will be using audio quality vibrators, like electrodynamic drivers, as you will see. We want our device to work in real time, and well, including the users from the beginning of the project will imply that we have to quickly iterate between development phases and tests, and we have to adapt to evolving specifications from the users. Okay, briefly about the timeline of the project. So we run on very limited funding and limited time, and this is how it worked. We had a first phase of the project during 3 days. We spent 2 days, two researchers, spending 2 days with a band of deaf musicians, so only deaf people playing music. They play mostly percussion instruments and bass guitar and sign language singing. So we were just observing what they were doing, what they're expecting from music, what they miss in music, what they want to experience through vibration. And then we had one day of testing with them, with deaf users and also hearing users. So we were testing like those vibrating flows that we made only self-made things using drivers onto objects and stuff. So we ended up with a first list of specifications, which was the starting point of phase number 2, which was the whole main part of the project. During 8 months, maybe we had 4 test concerts. During like actual concerts in this place here, you can see one of our partners is a music venue in Lille, approximately 1,500 seats. So we tested each version of our devices, and in between each test concert, we had a period of lab development. So at each test concert, we went back home with an updated list of specifications, which I will describe later. And some pictures of the concert, all the devices, laptop and stuff, and people trying to use our devices, understand the vibrations, and give us some advice on what they want to feel. And we were supposed to close the project with phase number 3 somewhere around March 2020. So we couldn't do it, obviously, because there was no room, no concert venue anymore. And we had trouble getting supplied with the electronic devices. So this is where we are. But still, I can give you the list of some of the specifications that we gathered from the users. The more complete list is in the article. From phase 1, so just observing the behavior of the musicians, we understood, our users made us understand that the devices must be, so the users must have some control of the device's behavior. Devices must be portable, so you must be able to hold the device while dancing or drinking a beer during the concert, for example. Our users were not interested in rhythm because they already felt the vibrations of the bass frequency, and they wanted to, for example, they saw a saxophone player playing a solo, and they told us, "I want to be able to feel this by vibrations." So they were more interested in the sound quality or melody, and we decided to focus on timbre. And the updated list of specifications during phase 2, for example. So the users gave us many ideas. For example, they wanted the vibrotactile signals, the vibrations, to kind of imitate some textures, when you slide your hand or finger onto different surfaces with different roughnesses. They wanted, for example, to beginning, we wanted to take all the audio signal, the full audio image left and right, and make vibrations from this. But they say, no, we're not interested in this. We really prefer to work on separate instruments, separate sources. So they can see all the instruments, but for example, I don't know, a violin player that doesn't produce any low frequency, they want to feel the vibrations of this source only. So they really wanted us to focus on separate sources, separate tracks from the mixing desk. And they also expressed their will to really choose the place in the body where to put the exciters and not have fixed solutions that they have to adapt to. So we have to adapt to what they want. Well, a few technical details of that important here and more details in the article. In terms of hardware, this is all the hardware that all fit in a medium-sized cloth bag like the HAID 2022 bag. Inside the bag, we have a wireless receiver that gets the audio in from the mixing desk. 2 input and 2 output sound interface that dialogues with a Raspberry Pi for the sound to vibration processing. An amplifier and 2 independent actuators that are the data and audio 25CT, if you know that electrodynamic drivers. Inside the Raspberry Pi, there is a not that clean pure data patch that takes the audio in, computes something like detects the onsets on the audio stream, or compute some audio features like the spectral centroid that I may describe later, and generate some textures, some waveforms. And here you can see that over the smartphone, the user can dialogue with the Raspberry Pi over Wi-Fi and RC protocol, and tune. I don't know if you can read anything here. Just set the output volume for the vibrations, the sensitivity of the algorithm to onset detection. I can choose the preset, one of 5 presets that we defined, and choose the audio channel for the input to be processed. Well, this is the last thing I have to say about what we did. How does the Raspberry the pure data patch work? What does it do? What we chose to do is what I call the symbolic approach, which would be to generate kind of the vibro-tactile icons, like auditory icons, waveforms that are driven by the features that we can extract on the audio stream. And we mainly focused on the spectral centroid, which is kind of the weighted mean of the spectrum, which tells us if this, roughly, if the timbre is bright or dull or muffled. Know this thing, but we're plotting the signal as quantifying how much bright it is. And that was really an interesting concept for the deaf people. So we try to render this bright side of the sound into vibration. So there are 5 presets that we implemented. First one, we take the audio in, we compute the spectral centroid, so brightness more or less, and we compare these to some fixed threshold. I don't remember the value. And according to if the spectral centroid is above or below threshold, we either generate this waveform or this waveform, both actuators. We have a second preset that has a fixed waveform here that is sent to both actuators with changing amplitude, and the value of the spectral centroid will control the position between the virtual position of the source between the 2 speakers using amplitude panning. So when the sound is, imagine you have one actuator here and one here, when the sound is very muffled or bassy, vibrations are produced here, and the brighter it comes, the more towards this actuator it will be generated. Preset number 3, again, the spectral centroid, or the brightness controls the balance between a kind of clean wave here and kind of a square wave and a very noisy signal. So you have the brightness of the sound that controls the noisiness of the vibration. Stepping a bit apart from the spectral centroid, there was a really interesting idea provided by one of the users. That guy saw a guitar player on stage strumming downwards and upwards and downwards and doesn't generate any vibration. So that guy wanted to feel something that is related to gesture. So we decided to produce something very simple. Okay. Each time, so every other time there's a downstroke, so we produce vibration that moves from actuator 1 to actuator 2, and every other time from 2 to 1. And then you have really an image of the gesture organization. And I guess I'm just going to conclude here. There is a 5th preset, which is quite different. So according to the onsets detected on input 1, we're generating this waveform on output number 1, and whenever there are onsets detected on input 2, we're generating this waveform into vibrator. And this is it. So we already have 6 devices available at this council venue. More are expected, and we're looking forward to being able again to do the tests. And project continues with a new founding. I can discuss this if you want. Whether in another project we don't use this symbolic approach anymore because we want something that is complementary to it. But yeah, it's going to be great. Thank you for listening.
Thank you. We have time for a few questions.
You mentioned that the participants wanted to be able to select the site on the body, the preferred sites, and did people sort of say we must distribute display so that they have on my arms, my back, my legs? Is there any concepts around that?
I think.
Sorry, could you summarize the question?
Yeah,
please?
I guess your question is just are there some general preferences about the location of the installation?
Yes, and more than one location. Was it ever considered to have it on the display on the arms, the legs, and the
So actually, and if there are more or less, remember, but I think I would be able to answer it. As you can see here, that's me, the blurred face, and you have the actuators that are hanging on cables, so you can put them everywhere you want, and so you can put one on the shoulder and one on the knee. You can do what you want. Preferred places where the hands, as expected. Yes. We also provide some gloves and some sleeves to maintain the vibrators, like here. You can see they're lighted, and but I think the preferred place was either the hands or maybe the chest. And interesting is that the deaf people, the signing deaf people, told me that it's no problem to hold with the hands the vibrators, even if they have to sign to communicate. They prefer to keep it to the hands.
Very short question.
Yes, I saw that you were using wireless communication. Did you have any chance to measure latency or honesty with the rate?
So the question is about latency on wireless communication. No, no, we didn't. It's just where is it? It's just controlling the volume and some thresholds for the onset detection or selecting one of the presets. So basically, we don't really mind the latency. But no, I have no figure to give you. Sorry.
Oh, so we have time for one more question.
It was a live concert with musicians, or it was pre-recorded?
Yeah, they were all. So this concert venue here has I don't know 4 or 5 nights of concerts per week, and we just show up at one night and we install all our devices and test it live. So like regular bands.
And you said you're not doing the mix down stereo, you're doing some channels, and with that part of who's playing on stage, I guess. And
yeah. Sorry for not repeating the question. This question is about how we selected separated tracks. So actually, so the concert is at 8. I come at 3, and I discuss with the sound engineers, and I choose. Well, this band has some interesting wind instrument that doesn't produce vibrations, and I select this one.
Thank you very much.
Thank you.
Next, I'd like to invite Francesco Dennis. He's going to talk about the Tickle tuner, the Haptic smartphone cover for Cochlear Implant users. Musical training. The floor is yours.
Great. So thank you, Jeremy. Good afternoon. I'm Francisco Ganis, a graduate student, master student from Aalborg University. And I'm here to talk about the Tickle tuner. There is a project that I carried out together with Professor Stefania Serafin and Mariana Batti. And what is a Tickle tuner? So it's a haptic smartphone cover that is meant to be used for cochlear implants users, especially for musical training. And the name comes from the Tickle toolkar, that is previous one of the first approaches to haptic feedback for cochlear implants users by Cohen, if I remember well. So before talking about the device itself, I want to give you a brief overview of what a cochlear implant is. That is basically a device that is able to restore hearing in people that has severe hearing loss, thanks to electrode that is implanted inside the cochlea and stimulates the cochlea and the auditory nerve with electrical impulses. And these are going then to the brain, and the brain is doing all the process. So in this way, basically, you're excluding the whole ear and somehow substituting it with some technology and some processes. There are several research that show that these devices are very effective in restoring speech understanding, but there are a lot of limitations in more complex sounds like music, and the appreciation of music is quite affected by this device, and because of a lot of different variables such as the age of the patient, the situation in terms of like the surgery, and a lot of other variables, the listening experience is very, very personal. So you cannot create a solution that works for everyone, but it's more like, again, a very personal experience for every cochlear implant user. So, as you might understand, this is a quite complicated topic, and we started talking and discussing about how to give haptic feedback, especially to the patients at home. And obviously, the first idea is to use the smartphone, since it's basically every one of us has a smartphone. And we wanted something that was easy to use, something plug and play, and maybe also easy and comfortable. So these are some of the initial sketches that we drew, and yeah, we moved then to the digital version. So we started actually first with clay for the handle, and then using photogrammetry, we reconstructed everything in digital, and we did obviously some iterations to have a better prototype. Talking about what is inside the shell, it's a very simple circuit. We have a USB-C that is connecting directly to the cell phone and retrieves the digital signal that is then converted by the DAC that is embedded in the device, the USB-C dongle. So the USB-C is feeding both the signal and also the power that is coming directly from the smartphone battery and goes to the stereo amplifier. One channel is for the audio that is going directly to the headphones, and the other channel is for the Haptic actuators that are two voice coil based actuators. So they have a very good, like they cover a very wide bandwidth, and they perform pretty well, I would say. I think, if I remember well, the brand is Hapcoil one. So this is the final prototype, how it looks like. It's very easy also to change some of the parameters from the software and reprint it and adapt it to a new cell phone. So it's quite easy to have a personal device for a different smartphone. And on top of the hardware, we also started working on some software. This one is some kind of like a prototyping environment that we designed mostly for ourselves. So to understand what kind of mappings, how can we transmit and communicate information through haptics when associated to music. We used pure data and MobilePlat. Pure data for the audio engine and the MobilePlat as a graphical user interface. And the software features some basic sound generators, such as sine wave, square wave, and so on. And then some filtering and the audio music player. The last screenshot here in the bottom, you can see another environment for pitch tracking. So you can retrieve different frequencies up to 4 and select the loudness of each frequency, and also, for example, octave down, and do some experiments with it. And there is also another button that is the amplitude modulation. This is what I'm going to talk right now. It is a mapping that we developed, also inspired by Park and Choi paper. And this is a mapping that we decided to use to convey pitch information. So what we are doing here is basically retrieving the fundamental frequency from the pitch tracking algorithm, and if this F0 is equal to a minimum frequency that we decide that we set, then we will have basically no modulation. While if the fundamental frequency is equal to a maximum frequency that we set again as a threshold, then we'll have the highest modulation that we decide, in this case 20 Hz. So you have, in simple words, for low notes, no modulation; for high notes, a very quick pulsation. And the carrier is the fundamental frequency. To try and to test this mapping, we decided to use a MCI test, a melodic contour identification test, involving 15 participants, normal hearing from our university on a voluntary basis. And we used 4 different instruments as a source, audio source, a piano, a clarinet, a viola, and the most simple, that is a sine wave, so only the fundamental frequency. And we were asking to associate 5 notes, that were basically melodic contours, and associate them to one of these images. Every melody had 1 or 2 semitones of distance between each note, and this was one of the screenshots of the test. We didn't give any information to the participants about how the mappings were done, so it was basically without any kind of training. And we were using also a cochlear implant simulation in the headphones. So what the participants were hearing was not the original sound of the instruments, but processed sound through a 8-channel noise encoder. This is, I want to say, it's quite a big approximation, because we really don't know exactly how the cochlear implants sound like. So this was more for trying to mask a bit the source sound, and especially for 1 semitone steps. It's very hard for cochlear implant users to understand the difference between 2 notes that are far at 1 semitones. So I would like to try to run 2 sounds. The first one is the one processed with the cochlear implant simulation. This is one of the contours, and I think it's very hard to say which of these ones is. And this was the original. So, as you might understand is quite tricky, and luckily it seems that the amplitude modulation helped quite a lot understanding the contour. So these are the results that we obtained, and with the amplitude modulation, we had an increase of almost 27% of correct answers overall, combining the 1 and the 2 semitones together. That is the first bar in on the left, is written AM. CI means instead that you have the full audio going through the haptic actuators, so the original sound. And the third one is no haptic feedback. So every participant had different combination of mappings in the handles. And as you can see, with the 1 semitone, as we were also expecting, the overall performances were a little bit lower. It was more tricky to guess and find the correct answer, find matching. While with 2 semitones, we had better results. Also with the amplitude modulation, because you have a bigger difference between the different notes. Yes. Yeah. For the same data set, if we look at and we divide it by the instrument, we can see that there is no significant difference between the audio of the handles and the no haptic feedback. So this shows basically that putting full audio to the haptics is not apparently helping a lot in understanding the pitch, especially the melodic contours, no matter what the instrument is. For the viola, there's, I think, one thing to mention is the fact that there is a big difference actually between the amplitude modulation and the other 2 mappings, because if you look at the spectrum of viola, the fundamental frequency is not very pronounced, it's quite subtle. So this information was lacking also in the simulation of the cochlear implant, and was very tricky actually to understand. So the amplitude modulation here helped a lot. While for the sine wave, there is only the fundamental frequency, and the cochlear implant simulation was performing enough well to convey the information of pitch, no matter the haptic feedback that was given. So yes, this was what I wanted to say to you. From now on, we will work on, we will continue working on this project. For sure, we want to extend the testing, since this one, we can say that is a preliminary test. We want to try it with the actual cochlear implant users. And I'm here for your questions. Thank you very much.
Thank you. So we have time for questions. Yes, please.
Because I didn't get quite why the haptic feedback would be specifically suitable for the cochlear, because I was thinking you could use it for deaf users, for example.
For deaf. Yeah.
Yes.
So
why is that a specific solution for the cochlear?
Thank you for the question. I've been asked why haptic feedback is suitable for cochlear implants, especially. So actually, I think there is no reason. What I want to say is that the project has been carried out in collaboration with Tickle Medical. There is a company that works with cochlear implants. So that's the topic that they are addressing. And that's why we focused on that target group. Cochlear implants in general, as I said at the beginning, they perform pretty bad with, for example, the pitch. So that's why we tried to address that problem. But I think that also, for example, using haptic feedback for other kinds of hearing impaired, like people that are using hearing aids, or deaf people again, are totally, I think, valuable target groups. So in this case, we decided to focus on a specific target group, but I think that it can be extended to other ones. Yeah. Yes.
I was just wondering about the stimulus, if you had tried resynthesizing or extracting sine waves from the stimulus or the recordings, and using that or replacing the original with sine waves, if that worked.
And send them to the haptic. Okay. Yes, I tried. So in the test bench.
Could you repeat the
question? Sorry. Yeah. I've been asked if extracting the fundamental frequency from original's audio file is working, and yeah, the answer is yes, it's working. It's actually what is happening in the pitch tracking algorithm. So if we are loading in the audio player a simple audio file of an instrument recording, you can extract the fundamental frequency and directly send it to the haptic actuators. It's working with a pretty low latency. I didn't measure it, but it's like I'm using pure data, and the embedded object is fast enough to not have any kind of like latency issue. For the test, we preferred to use instead like synthesized haptics. So we were associating the original file that was a MIDI file with built pre-made haptic, to not having any kind of like issue in terms of like frequency mismatch or something like that. So we decided to have more control on synthesizing on MATLAB, for example.
Oh, questions? Maybe I have a last one. So you mentioned that it's a training program,
Yes.
but is that the hope that after doing that they won't need a haptic, they'll be better at pitch, or?
That's a very good question. We don't know. We don't know. It's I think too early to say this. The hope is to maybe be able to convey extra information, and with a long training, maybe they won't need any more than haptics. But this I really cannot say in advance. I hope so. Yeah.
Maybe last question. Why the stereo? You seem to be sending the same signals, or you're sending different haptic signals?
Oh no, I'm sending the same signal. Right now we are using a stereo amplifier, so we are bounded to a dual mono configuration, to having on one channel the audio and the other the haptics. At the beginning, we tried also to send different signals on the actuators, but we tried a bit, and like for how the device is built, there is communication and rigid communication between the actuators. So you cannot really say if it's coming from the right or the left actuator. There is a subtle difference. So for now, we are working on one configuration.
Thank you very much.
Thank you.
As I understand, our next speaker will be online. It's Charlotte Reed. So I don't know if you can hear us and if you can share your screen. You do it. That's your job. Charlotte, can you share your screen? Can you say something so we can hear you?
Yes, hi, good morning. Can you hear me?
I'm Bailey.
Oh, let's see. Can you hear me okay?
Yes.
Okay.
Do you want to turn on your camera, or is
Okay. Okay. Should I begin? Yes.
Yes.
Should I begin? Okay. Good morning. Good afternoon, everyone in London. I'm sorry not to be able to join you for the conference, but hope that you all will enjoy the exciting program put together by Karis and Ildar, and hope to see you at the next meeting. The work I want to talk about is research we've done on a phonemic-based tactile supplement to lip reading, and to share our findings, initial findings on consonant identification. My co-authors are Dmitry Konevsky of Google Research, Jay Deloge, and Juan Martinez and Hong Tan of Purdue University. And Hong Tan is actually attending in person, so you can catch up with her if you want to continue discussions of the work. So the motivation for our research was in the area of accessibility and is concerned with improved speech communication for persons with profound deafness. Although many deaf people, capital D, communicate with sign language, there are other people who rely on speech communication. And the particular population that we are addressing here is are deaf people who rely heavily on lip reading to understand speech, but do not derive benefit from a hearing aid or cochlear implant. Perhaps they're not a candidate for a cochlear implant or do not derive benefit from it. So our basic approach is that we start with the baseline of lip reading. So the deaf person is watching a person who's speaking and getting information about the speech signal just from the movements that occur on the lips. There's some information there, but it's very imperfect. And our goal is to supplement lip reading with haptic cues that are designed to fill in the gaps that lip reading doesn't provide. So basically, even though this is an audio haptic conference, we're talking about multi-sensory integration of visual and haptic cues. And our goal is to develop haptic cues that disambiguate lip reading that can be easily combined with the lip reading signal and will result in a perfect speech reception at the level of the phoneme. And the hope is that with this phonemic level information, that this will transfer to understanding speech in context. Okay, let me go to the next one. So the background for this work is that it's kind of a spin-off of previous work that was conducted in collaborative work with Purdue and MIT, Professor Tan's group and my group at MIT. In that work, we developed a tactile phonemic sleeve that we call TAPS. And the purpose of that was for reception of speech through the tactile sense alone, using a phoneme display, a tactile display of phonemes. So that consisted of a 4x6 array of vibrators that were applied to the forearm. And we coded as unique tactile signals each of the 49 English phonemes, and found that our participants could learn to identify the phonemes after 4 hours training with 86% accuracy, and that when we combined phonemes into words, that the tactile words were acquired by the best subjects at a rate of roughly 1 word per minute for a 500-word vocabulary. So the second author, Dmitry Konevsky, of this work, knew of this work we had done, and he proposed to us that we work on a pared down version of the system that would be devoted as a tactile aid to lip reading. So Dmitry has been profoundly deaf since childhood. He does not use a hearing aid or cochlear implant. He has in the past used different kinds of tactile aids. He uses the Google speech to text application and was involved in working on that. And he uses that quite a bit so that he can understand speech by looking at the text on his phone. However, he told us that he felt it was a real limitation not to be able to look at the talker's face while you're communicating with somebody, just to get the additional kinds of cues that are present on your face, emotional types of things, etc. So in conjunction with Dmitry and his group at Google, we we worked on a tactile aid to lip reading. And I want to say that in the studies that I'm going to present, that Dimitri, is the subject in this work. So the first thing we wanted to know was, if we're going to supplement lip reading, what was the lip reading performance? What did that look like? So the first thing that we did with our subject DK was to do a consonant identification through lip reading alone. So we had audiovisual recordings of 22 consonants in CV syllables in the vowels with the vowel E, on, U. And these syllables were presented in the context, you will mark pa, please, or you will mark ba, please, whatever the syllable was. So there were 4 different talkers, 2 male and 2 female. And we did the testing with a 22 alternative forced choice identification test where a syllable would be presented and the participant sees one of the stimuli, and chooses one of the responses. These were audio-visual recordings, but they were played out only the visual part. We didn't use the audio. So in doing this test, after many trials across these talkers, the overall percent correct is just 32%. So you can see that the lip reading does not provide a very complete picture of the consonant phonemes. So we put the data into the form of a stimulus response confusion matrix and analyzed it with a hierarchical clustering analysis to see what sets of sounds were grouped together. And so here's the result. The hierarchical clustering analysis produces a dendritic tree, and the smaller the distance on the y-axis, the closer two sounds are perceptually, meaning that they are frequently confused. And through this analysis, we see that there are 7 clusters that emerged from the analysis, and we call those visemes. And I'm just writing down what was along the x-axis of that group of that previous slide. So there's 7 different groups, and for example, I'll start with P, B, and M. These are 3 bilabial sounds are made by bringing the lips together, and they simply can't be told apart on the lips because there's no information about whether it's a plosive, a nasal, voiced, or unvoiced. And so on through, there's 7 different groups. They're called viseme groups, meaning that they're visually equivalent. So I just want to note that among the different groups, the distinctions are seen primarily on the basis of a place of production of the sound. For example, P, B, and M are all made at the front of the mouth, whereas S, Z, T, and D are in the middle, kind of made in the middle of the mouth. So you don't confuse P, B, and M with S, Z, D, and T. But those sounds are difficult to tell from each other. So there are, it's mainly the place of articulation that determines what goes into the vising group. There are some distinctions among different manners of production, but the voicing feature of speech does not convey at all through lip reading. And this carries a pretty high load in English, and it's be good to have that piece of information to improve lip reading. So I just want to talk about some points that we used in the design of the phoneme-based tactile aid to lip reading. First, the goal is to create tactile codes to distinguish among the phonemes within each viseme group. So we use a phoneme-based approach, and we assume that there's automatic speech recognition at the front end of our device, and that the output of the ASR, the speech recognizer, is a string of phonemes corresponding to the spoken message. And then each phoneme we will assign a tactile code to. The tactile codes are then integrated with the visual lip reading signal to result in a unique tactile plus lip reading signal for each phoneme. Note that tactile codes may be the same for different phonemes as long as the phonemes themselves are in different vising groups. And we designed the tactile codes to exploit what we know about the perceptual strengths of the tactile sense. And this came out of the work that we had done previously on the tactile alone device. And I'll talk a little bit about that when I describe this display. Another point I want to make is that in speech, there's a lot of token variability from different speakers and different utterances within the same speaker. And that the token variability in this case of using automatic speech recognition is that that's handled by the recognizer and that burden isn't put on the user of the tactile device by making the tactile signal vary with each production. Instead, the tactile signal remains constant anytime a phoneme is identified. And then, so then we encoded the phonemes through 6 channels of a tactile display, which I will show you here. So we had a display with 7 wideband tactors. The first 6 channels were applied to the dorsal and ventral forearm and used for coding the phonemes. And the channel closest to the wrist was on the palm, the thenar eminence, and it carried a speech envelope signal. So in using this device, the user places their hand palm down on the lower row of vibrators such that the palm is on vibrator 7. And then the ventral surface of the forearm from the wrist to the elbow occupies the rest of the other 3 phonemes. Then we fold the top part of the device over so that vibrators 5, 3, and 1 are on the dorsal surface of the forearm, and we then strap it down with Velcro straps. And this is a pared down version of the 24. We had 12 and 12 in the original device. Okay, so I want to give examples of tactile codes for 2 of the vising groups, and then just from this tell you the general principles that we used in developing all the tactile codes. So take the group B, M, and P, ba, ma, pa, which are basically impossible to tell apart on the lips alone. So we coded B and M on using Tactor 5, which was the dorsal vibrator closest to the wrist. And the carrier frequency was 250 hertz, was no further modulation for B, but M was that same signal with a 30 hertz amplitude modulation. And for P, the cue was the lack of a tactile cue. Then then below that is a phoneme, is a vising group that has la, ya, na, ga, and ka. And we coded those with 3 different tactors 1, 2, and 5, 2 different carrier frequencies, 60 hertz and 250 hertz, and with and without amplitude modulation. So basically this covers the parameters that we used in generating the codes. There was the location, which was the tactor that was used in the stimulation. We used 2 different carrier frequencies, 60 and 250 hertz, and the carrier could either be amplitude modulated or not. I want to point out that that we can use the same tactile code for 2 different sounds, like M and N are the exact same tactile code. However, those are never going to be confused through lip reading alone, where being in different vising groups and M being made with the lips coming together and N being made farther back in the mouth. So, okay, so we set up to combine the tactile cues with lip reading and to conduct consonant identification tests on the participant. So we used, to start out, we used what's called the Montreal Forced Aligner, which does a non-real-time phoneme recognition. That gave us a perfect phoneme recognition, which meant that we weren't confounding the accuracy of the recognizer with the ability of the tactile cues to convey information. So we got the phoneme recognition, and we also knew the duration of the tactile code in the recognizer. So we used that to determine the length that the consonant code was displayed. The tactile signals were presented at a level of roughly 20 dB above threshold with loudness balanced across the tactors. And it was highly important to have very good synchronization of the tactile codes with the visual stimulus, which we did. The speech stimuli were presented in the context, you will mark pa, please, for example, and tactile codes were presented for every vowel and consonant phoneme in the phrase, even though the subject was only asked to pay attention to the consonant in the syllable, in the CV syllable. So the participant received training on identifying the consonants with tactile cues combined with lip reading. The training was conducted with sets of viseme groups, and we gradually combined them over the course of training to form larger sets as the training advanced. And we also obtained performance for lip reading alone for each group so that we could compare the benefit of the tactile aided lip reading to lip reading alone. So just to talk a little bit about what we did for training in learning the codes. So we had 11 training sets, which I'll show you in a little bit. So for each of the training sets, we first showed a schematic of the tactile aid with little description of the codes for the phonemes in a given set. And then we had the ability to play isolated versions of that tactile code under the participant's control. And then we played the speech stimuli, lip reading plus tactile, the visual speech stimulus plus the tactile codes. We played them in a given order that the subject knew, the fixed order that was being presented, and they could ask for repetitions and try to focus in on the tactile cue and to integrate it with lip reading. So after that, we did consonant testing where we randomized the order of the presentation with correct answer feedback and continued this with different runs until performance was at least 80% or had begun to saturate with showing no improvement with further training. And after that, we then conducted post-training testing in which we did the randomized order presentation of the test of the stimuli without correct answer feedback. And the subject had the option of repeating the stimulus on each presentation. So this is a description of the 11 sets that we used, the number of stimuli in the set, and then the number of training runs. And then we also have the total number of training trials and the maximum score that was reached in the training. So as the subject began with relatively few trials, reached 100% correct on the first 4 sets that we tried. As the sets start to combine, the number of stimuli in the sets increases, and it took more trials to be trained on it, but still not tremendous amounts. And let me see, I don't have, let me go back. I messed up. The bottom 11, which is not showing on the slide, is the full set of 22 sounds, at which performance reached 79% with relatively little amount of further training. So the next slide shows the post-training scores. on the 11 stimulus sets, each of the 11 stimulus sets. And the lip reading performance is shown by the level of the blue bar, and then the performance with lip reading plus tactile is shown by the height of the red bar. And so the red shows you the benefit in percentage points that was given by the tactile aid. And in all stimulus sets, there was a large amount of benefit. And when we get to the final set, which had all 22 consonants, it's about a 30 percentage point benefit from about 40, maybe 42% correct to like 73% correct with the aided, with the tactile cues. So just to conclude and talk about future work, with this initial set of tests on our the subject who asked us for the device showed that he was pretty successful in learning to integrate the tactile cues with the lip reading signal, and with relatively little training, the device was effective in improving his consonant performance over lip reading alone. Our ongoing work is concerned with the development and evaluation of tactile codes for vowels as supplements to lip reading, further training and testing with additional participants, both hearing impaired and normal hearing, and extending our evaluations of the tactile aid to connected speech materials. In future work, we would hope to develop a wearable version of the device with real-time processing and potentially using signal processing to extract speech features for real-time phonemic identification. And I'd like to thank the sponsors of our research, which were awards from Google and NSF grants to Purdue and MIT. Thank you very much. And as I said, Hong Tan is on site, and you can talk to her further about the work, but I'll be here for any questions you might have. Thank you very much.
Thank you very much. Unfortunately, you ran a bit out of time, so we won't have much time for questions, but I'm sure people will be able to write to you. Just have maybe a very small question. So you mentioned that you want to have that to work in real time. How is that possible? Because even with the best phoneme extractor, you still need to have the time for the phoneme to be said. So you will always have a delay by definition.
Yeah, we think that we think that the processing can be fast enough to accommodate the amount of delay that people can tolerate between audio visual or tactile visual. Yeah, we think that's solvable.
We'll love to see that then. Thank you very much.
We can have.
Okay. Yeah. So.
Actually, I'm sort of wondering a little about design inspiration. So maybe you already did that, but I mean, I know that there are methods where you complement lip reading with touching either the shoulder or the neck, or maybe even the lips. And I would have kind of thought that it would be interesting to see what is it that you pick up when you do that, and how that complements the lip reading. And also that kind of tells me that the fingers might be a very good spot to present the vibration. Yes. I was just wondering if you had been looking at those kinds.
Yeah, no, I have studied the Tadoma method of speech reading that's used by people who are deaf and blind, and we have data on consonant and vowel and sentence perception by those, and that sort of forms a benchmark to which we can compare all other tactile systems, because it's a very good method of communication for the people who have learned to use it. And the other question was, I forget.
The question was more that if you use that as design input when you were designing the system, how to, or if you just designed this completely separately.
Oh, but well, often you might want a hands-free device because hands are used for other things, and so you know can use the arm for display, and not occupy you know the hands that are needed for other things.
Thank you very much.
Thank you very much.
All right, so thanks very much, Jeremy, for chairing the session. What happens next is that at 5 p.m. we are starting with our first keynote, but in a different space where also the concert and the reception are going to be held. So there are some of our volunteers who will guide you to that other building. It's called the Arts 2 building, in case anybody wants to go independent. So yeah, please start
All right, hello there. Let's do a check here. Hey, shall I share my screen and see if this is working properly? I'm gonna try this, share this. Okay, then do you see my screen? Oh, okay.
Hi, Andrew. Still checking quickly the sound, and I'm gonna introduce you. Why is there? It's fine. We think if they cannot see him in the big screen, it's fine. So we ask him to say something.
Hey, I can hear you fine. Can you hear me?
Yes. Yes. Okay.
All right. Good. I can't see you because I've got my presentation turned on, but I can hear you and I can also see the chat.
Okay. I think it's good.
Can you ask Andy to speak for a bit? Hey Andy, can we test your loudness? Can you say
Yeah, sure. You want to test the the level of my mic, you mean? Well, testing 1, 2, 3.
yeah, can you say something?
Okay, well, all right. Checking sound levels. Here we go. Hopefully this sounds okay on the other end.
Okay, volume's okay. Volume's okay.
Yeah.
Yeah, okay. Louis got you.
Okay, great. Cool. So are you in the film and drama studio?
Yes. Can you hear me? It's Harris.
Yes, I can. I can hear you. Yep.
Right. Okay. Are we good? Can I begin?
Fine with me.
All right. Okay. So
Well, the mic is on, it's on the computer. It's on. Which channel is it on?
we don't
No
know.
channel, it's just for the Zoom. It's just for Andy.
Okay.
Yeah. All right. So it's cool to hold the microphone because it's not working for you, but I think it's working for Andrew. So yeah, welcome for our first keynote for HAID 2022. So I'm very, very happy to introduce Professor Andrew McPherson, a computing researcher, composer, electronic engineer, and musical instrument designer, and a senior research fellow of the Royal Academy of Engineering. He's professor of musical interaction here at Queen in the Center for Digital Music at Queen Mary, and he leads the Augmented Instruments Laboratory, who later on you will experience as they organize the concert for tonight. Andrew holds undergraduate degrees in both engineering and music from MIT, an MNG in electrical engineering from MIT, and a PhD in music composition from the University of Pennsylvania. His musical instruments are widely used by performers and composers across many genres, and his research has led to 2 spin-outs. Augmented Instruments Ltd, which develops Stella, which many of you are familiar with, and some of you participated in the workshop earlier today. Bella is an open source audio maker platform, and the other spin-out is Touch Keys, a transformation of the keyboard into a versatile multi-touch control surface. He's deeply committed to teaching. Bella is used in the classroom by over 20 universities today, and he has an online course on audio programming that has been followed by learners around the world, around the globe. And I should say, I should give a little bit of a personal task after reading the official bio. I met Andrew in Düsseldorf during an art experimental music festival around the end of 2018, I think. Anyway, so he was one of my first contacts here at Queen Mary before I finally, about a year and a half later, joined the same group. We are about to start supervising together a new exciting project on interaction, music, deep learning, and maybe haptics at some point. That's for me. Thank you again, and Andrew, the floor is yours.
All right. Well, thank you, Horace, for the generous introduction. And yeah, it's I'm sorry that I can't join you all there in London. Obviously, that's usually my home base, but I come to you from Portland, Maine, where I'm away for a couple weeks. But hope the rest of the conference is going well. And yeah, of course, please stick around for the concert after this tonight, organized by members of the lab. So I guess I don't need to introduce myself at this point, thanks to that very nice introduction. I'd just like to introduce the lab, the Augmented Instruments Lab. So this is part of the Center for Digital Music at Queen Mary. And I've just been so lucky to work with such fabulously talented people over the 10 plus years that I've been at Queen Mary. Here you can see the current membership of the lab, PhD students and postdocs, including people working on the AI and Music Center for Doctoral Training, which is currently running at Queen Mary, and just a really wide variety of topics around musical instruments and interaction, and the kind of technical and cultural processes around creating interactive technologies. If you want to know more about what's going on at the lab, you can check out the lab website, instrumentslab.org, and there you can find more details of our projects, papers, and such things. You'll note here that you can see Bella as one example of a project that has come out of the lab. I'm actually not going to talk about Bella at all in this talk, nor touch keys for that matter, but instead maybe going to look at a little bit of a higher level view of what's going on in the kind of musical instrument and digital technology sort of space. Essentially, this talk is about instruments, and the term instrument itself, I think, is actually quite complex when you dig into it. And it depends who you're talking to, because to an engineer, a musical instrument could serve as a transducer. It converts the performer's actions into sounds, and potentially other modes of feedback. But to the psychologist, an instrument might be a mediator, something that extends the performer's mind and body, shaping their action and their perception. Whereas to the ethnomusicologist, the musical instrument is the product of a social and cultural context. And these things can all simultaneously be true. And I want to dig into each of them in just a little bit more detail. So if we start with the technical view of a musical instrument, something that takes motions, actions, gestures as input and produces sound as output, we discover that this is actually quite a complex process and actually a very difficult one to design. I really like this quote from the HCI pioneer Bill Buxton, who wrote back in '97. He said there's 3 levels of design. You have your standard spec, you have your military spec, and you have your artist spec. And the third of these is the hardest and also the most important, but if you can nail it, then everything else is easy. Now, what's all that about, right? Why is it so difficult to satisfy the needs of musicians? Well, it's clearly not difficult to make a device that takes in some actions and produces some sounds in response. But if you consider what a professional musician expects out of their instrument, it is an incredibly challenging specification in terms of spatial and temporal precision, in terms of the dimensionality of control, the fact that you don't just have one sort of sensor element, but the entire object can be both a sensor and a sort of a sound radiator. The entire system is nonlinear, which makes scientists and mathematicians a bit grumpy. And then you also have multiple modalities, especially audio and tactile channels. And you have to do all that with 100% reliability if anyone is going to be willing to take it on the stage. And then if that wasn't enough, you also have to consider that nobody comes at a musical instrument in a total vacuum. There are skills, there are expectations, both personal and cultural. And I'm going to talk about those more in a minute. But let's have a little bit of a look at the kind of a very rough state of the art in terms of where we are with this sort of audio and haptic instrument design space. One thing that we've done very, very well in the last 10, 20 years is making really good models of musical instruments. So you can make quite a sophisticated mathematical model of a violin or a guitar or a drum or anything else. And these can be quite complex. They can have a lot of different control parameters, and ultimately they simulate the vibrations of the instrument and produce as output an audio signal. And it can be challenging to run these in real time, but we can throw enough GPUs at it and we might be able to do okay running it on some sort of high performance computer. So what's the problem? Well, the problem is this. We still have to play the instrument, right? We still have to interact with it somehow. And the question is, how do we capture the richness of interaction that a musician brings to their instrument? not an easy challenge at all, because it has nothing to do with mathematics and everything to do with interfacing and sensing. So what we often end up with instead is something kind of like this. Here is how we control this really sophisticated mathematical model with a really cheap interface designed 40 years ago for a completely different context. And it's like, you know, having a beautiful world inside of a bottle with a very narrow neck, and all you can do is sort of peer in, but you don't actually get to explore it properly. In other words, one of the key challenges in digital musical instrument design is physical digital integration, the boundary between the physical and the digital worlds. And this is both a sonic issue and a haptic issue, and ultimately it's an issue of interaction in a sort of bidirectional sense. So that's the technical view. Back then to the next view, which is the instrument as a mediator. Now, there's a really nice body of literature that is emerging around the relationship between musicians and instruments. And this paper, which I like very much, talks about how a musician no longer experiences the boundary between herself and the instrument. And this is, of course, a product of expertise developed over many years, that the instrument comes to be seen and felt as an extension of the body, so that you can kind of think through the instrument to the thing that you want to do, rather than having to be very consciously aware of these actions. And there are psychological and neuroscientific bases for these kinds of experiences. But ultimately, what we're talking about here is sensorimotor skill, sensorimotor learning. This kind of effect doesn't emerge overnight on a new instrument. And then finally, we have the instrument as a musical ecology. And here I quote this paper from Simon Waters, which I like very much, talking about how a musical instrument is not an object, but a process. It's a dynamic system in a constant state of change, seasoning, adjustment, and decay. So the idea is that to consider the instrument only as a technical object is clearly, too limited. But even the idea of the instrument and the performer as a sort of bidirectional relationship is too limited if you're not also considering the surrounding cultural context, the expectations of the performers, the composers, the audiences, etc. And ultimately, this shapes the identity of the instruments we build. So that's the kind of overview of what's going on in this space. But maybe before we dig into any specific examples of instruments, we could just ask this question. Do we really need any more instruments anyway, right? I mean, there's a lot of instruments out there. We certainly don't lack for the ability to make music. Sergi Jorda wrote in 2004, many new instruments are being invented, too little striking music is being made with them. 20 years on, I don't think that situation has changed. It's really, this is really an ongoing issue where, in a way, we can actually build the technology faster than we can learn to play it, and faster than we can invest the time to really make detailed, extensive musical contexts around the instruments that we're building. But maybe rather than asking kind of what's wrong with new instruments, let's ask instead, well, what's so good about old instruments? Why are we still playing these wooden boxes with strings on them when we have digital technologies instead? And there's lots of answers to this, of course. Some of the answers include the time it takes to learn an instrument. If somebody's going to spend 20 years of their life becoming expert on a violin, not very likely that they're going to do the same thing on a completely new and untested technology. You also have the virtuoso performers who can serve as role models for people to learn an instrument. You have established repertoires for existing instruments, and you have pedagogical practices which can help teach new students to play these instruments. And ultimately, we could kind of group these things into two categories. We could talk about our sensorimotor skill, which is fundamentally an individual issue. And then we can kind of lump the rest into this notion of musical culture, whatever we take that to mean. But a key property is that it is a collective phenomenon, not something localized to an individual. Maybe in short, we could say that instrument design is not about the technology, or at least not solely about the technology. It is primarily about performers, and it's about culture. One suggestion that I have for that is that existing musical practice can be a really valuable resource when designing new instruments. Now, I don't mean to elevate traditional practices over new ones, and I don't mean to suggest that we should all just be building emulations of the piano for the rest of time, but that sometimes there's a really rich space to be explored when you have one foot in a familiar tradition and one foot in something that is new and unexpected. It is worth thinking a little bit about what musical values are encoded in that process. Anytime we make an instrument, no matter what we say about it, we are making judgments about what we mean by music and whose music that is. So some questions that we might ask would be, in what context would the designer expect an instrument to be played? Or also, what aesthetic ideas does this instrument suggest to the performer? It's all well and good to say, well, this instrument is for making any kind of music, or this is just a free creative tool for people to do what they want. But even the most unrestricted interface is going to have certain things that it makes easier or more obvious than other things. Thor Magnusson has put this very well in this article from 2009, where he talks about the ideology encoded in instruments. For example, the piano keyboard tells us that microtonality is of little importance, or the drum sequencer tells us that 4/4 rhythms are the most natural, or the digital audio workstation tells us that it's perfectly normal to repeat the same performance over and over in the same track. So when we make a new instrument, this is a really important thing to consider. And I'm going to come back to this in a little bit more detail toward the end of the talk. Now, in terms of the blend of the old and the new, one approach that I've had to it, which the lab name now reflects, is the augmented instrument. This is essentially an existing instrument which has had something extra added to it. So in this conceptual diagram, let's suppose that the blue circle is the space of techniques that we could perform on a traditional instrument. The ideal augmented instrument lets us do all of those things and more. But of course, in practice, we very rarely gain something without giving something up, however subtle or non-obvious that might be. So we usually get something a little bit more like this. But that's fine, because the additional techniques that we get are usually creatively inspiring if we've done our job right. I'll tell you about one example of an augmented instrument, and this is actually, for me, in my career, kind of where this whole area of research started. This is the magnetic resonator piano. I started this project in 2008, and it is literally an acoustic grand piano, but it's more than that, because inside of it, we have these electromagnets. The electromagnets are designed to induce vibrations in the strings without being struck by the hammers. And this opens up a whole different world of sounds that we can explore, but we need a way to play it. And so there is, at the back of the keyboard, an optical scanner, which measures the position of each of the keys in real time. And this is not just a MIDI scanner with note on, note off. It actually measures the continuous position of the keys, which I'll talk about more in a minute. And then a familiar property of digital instruments is that we need some kind of translation or mapping between the sensor elements and the sonic elements or the other forms of feedback that we have. And getting this right can actually be extremely important. So before I talk about this in more detail, I'll just play a video to give you an introduction to the instrument. I hope the bandwidth of this connection allows for this to play in reasonable fashion. If not, of course, you can find this video also on the lab website. All right, so that gives you an idea of the sound world of this instrument. Let's talk tech for a minute. So here's how it works. Basically, piano strings are made out of steel. Steel is what's known as a ferromagnetic material. That means you can stick a magnet to it. Now, just holding a magnet over a string isn't going to produce anything interesting, but an electromagnet lets us apply a time-varying magnetic field to the string. And so by switching the magnet on and off at the natural frequency of the string, it can be made to resonate. And so the idea is that when the electrical current is on, the string is pulled up toward the magnet. You turn it off, the string goes back down, you turn it on again, and so forth. And in this way, you can cause the string to ring at any combination of its natural harmonics and elicit a number of different sounds out of the instrument, depending on what signal goes into that magnet. Here's a picture of what this looks like in practice. You can see the electromagnets here. They're mounted on these brackets so that you can slide it back and forth and adjust the positioning for each different piano. Each magnet is driven from its own amplifier board, and there's a whole signal routing system that this is covered in some of the papers early in this project, but I won't talk about it here. Instead, here's a close-up of what's happening between the magnets and the strings. What's happening is an air gap of about 1 to 3 millimeters. Basically, we put the magnets as close as we can to the strings, but not so close that they touch, because that'll make a nasty noise. And yeah, I mean, that's probably enough of an overview of the electromagnets. In some ways, I think the character of this instrument has just as much to do with the way that it's performed as it does with the electromagnets, because this is far from the only electromagnetic piano. It's not the first one, it won't be the last one. And but what I think sets the magnetic resonator piano apart from some of the other projects is the relationship between the performer and the instrument. And the issue that we have here is that even if we can continuously induce vibrations in the piano strings with electromagnets, that's only as good as how we can control it. And if we're still using a MIDI keyboard, we have the same kind of usual problems, which is that we have a note on message, a note off message, and maybe some slightly awkward continuous controllers in between, but it's not really kind of natively designed for the sort of subtlety and nuance that you might get out of a string instrument. You can argue with me about that afterwards, but I'm a string player, so my biases show through. What I've done is build a scanner which is designed for continuous key angle. And I started with the Moog piano bar. The Moog piano bar was a commercial product in the early 2000s, which was a MIDI scanner for the piano. You drop it at the back of the keyboard. It's got some LEDs and photodiodes that are measuring the amount of reflected light off of the keys, or in the case of the black keys, the amount of light that passes from one side to the other. And from that, it will give you a MIDI signal, note on, note off. Now, I thought, well, okay, even if MIDI isn't what we want, surely inside of this device, there must be the raw position measurement somewhere. And there was. And so it turns out that you can pull out the raw key position values and digitize them. And you can get things like you see on the right-hand side of the screen here, where that's a single key press. And you see the trajectory and the acceleration of the key as it goes down. You see this kind of raised top in this blue plot, which shows some pressure exerted into the key bed. The key is moving a little bit because there's felt underneath and you can push on it. And, and a number of other features as well. The other thing this kind of sensing lets us do is implement extended techniques like vibratos and little taps and kind of halfway presses and things like that. Now, more recently, I've set out to try to build more of these instruments, and the piano bar and its scarcity has become the limiting factor. So together with Giulio Moro, I have engineered from the ground up a new keyboard scanner, which is designed natively for continuous key position. And so this has all of the same kind of features, but is designed to support this in a more kind of robust way. And it has RGB LEDs because why not? And it folds in half because it was annoying to haul the piano bar around all the time. So if you want to know more about this, we're actually kind of getting to the point of releasing this sometime soon. So drop me a line if you want to learn more about this scanner. And then finally, we have here gesture to sound mapping, the translation between what happens at the keyboard and what happens inside the piano. Now, I did not want the MRP to feel like a computer-based instrument in the sense that you had to think about what the computer was doing or you had to interact with a screen. It should have the property of a traditional piano, that you just do something at the keyboard and the sound comes out and you can kind of think through it rather than thinking about it. This led to a few decisions, for example, to kind of preserve the traditional idea that one gesture produces one musical event. And it also led to 3 goals, which are not entirely mutually compatible. One of them is to preserve all of the existing piano technique, to add some new techniques for continuous note shaping, but to have the whole thing be no harder to play than it ever was. Because as we've talked about, that the learning time can be a real barrier to building communities around instruments. So the design of the instrument becomes an optimization between these things. Some principles that emerged out of that was to be able to play traditional piano and the resonator system at the same time. And this kind of idea that I would describe as, kind of normal gestures produce normal sounds and weird gestures produce weird sounds. And again, there's more detail on this in some of the papers about the instrument. Basically, what I'm saying here is that augmentation is never free. When you add new techniques, it can limit old ones or take time to learn. And so what we try to do is to maximize the creative novelty while minimizing the amount of learning time that would be a barrier to people using the instrument. So if we go back to our little diagram here, we have traditional piano technique, and what the magnetic resonator piano adds is a whole set of things around sustain, crescendo, vibrato, timbre changes, harmonics, pitch bends, etc. But at the cost of some changes to the role of the keyboard. For example, holding a note down with the pedal and holding a note down with the key no longer produce the same sound, because the latter of those causes the note to sustain with the electromagnet and the former does not. We need to make some decisions about whether and where to use the resonator, and there are some unfamiliar techniques that need to be learned. But ultimately the new sounds, I think, is what justifies the expenditure of effort to compose for the instrument and to learn to play it. Now, the way that this ultimately unfolds is oftentimes quite different than what I might have expected as the designer. And I could give a whole talk just about this. I won't, so you're welcome. But I will quote Thor Magnusson again, who talks about instrument makers actively designing affordances, basically things that you can do with the instrument. And I just told you a bunch of them. Oh, I think this instrument does extended sustain and crescendos and pitch bends and whatnot. When the performer actually encounters the instrument, they might care about that stuff, or they might not. They may just want to kind of feel around and get a sense for how far can I push it in this direction? What happens if I do that? Oh, can I make this kind of thing happen? And you end up with some surprising results. So I'm going to play you here a little excerpt of a piece by the pianist composer Xenia Pestova Bennett, who has been a real champion of this instrument and has done some really cool things with it. This is a piece called Glowing Radioactive Elements, and Xenia has discovered some really surprising sounds inside the instrument, which I'll tell you about after this excerpt. All right, well, I'll stop it there. The entire video of at least 3 of the movements of this piece is on the lab website. What was going on there? Basically, Xenia discovered a kind of I don't know, a kind of gap or almost a sort of bug in the instrument, if you will. There's noise on the measurements of the key position, which interacts with the software in a funny way, causing it to kind of jump back and forth between different modes, and that produces a really kind of unusual signal into the electromagnet, which then is put into the string at the moment that the damper is just barely lifting off the string, and you end up with all these really strange, unusual scratchy noises. And that became the basis of a movement of this piece. Quite obviously not something I had designed into the instrument, but the problem ultimately then is when I want to do a new generation of the instrument, for example, this new piano scanner, it becomes necessary to actually figure out the kind of brokenness of the original one and emulate it somehow, because otherwise these effects, which were entirely unintentional, end up going away. And this is a story that actually repeats time and time again throughout the history of musical instruments. But anyway, I'll leave the MRP there, and I'm going to tell you about a couple other projects. Back to this question of sensorimotor skill versus musical culture. Sometimes in designing a new instrument, it can be a little bit unclear about kind of which aspect of these things is the most important, given limited design time. And a few years ago, Jacob Harrison, Robert Jack, and Fabio Morreale, members of the lab, set out to try to untangle these things somehow. And we did it in the context of the guitar. We were asking specifically, what is more important? Is it more important that a digital guitar behaves like a guitar in a kind of sensorimotor aspect, or is it more important to kind of capture the kind of cultural significance of guitaring, if you will, all of these things around the guitar? Now, to illustrate the latter point, Jacob had come up with a series of little videos. Some of you who've seen my talks before have probably seen these videos, but I will ask you rhetorically, since I can't see your responses, which of these 4 videos you consider to be the most guitar-like. Here we go. Here's number 1. All right, here's number 2. Number 3. And then here's number 4. All right, so you can make up your own mind about which of those is the most guitar-like. What I find interesting is that there's a lot of disagreement about that. But another thing that's interesting to note about these is just the role of skill in all 4 of these performances. I mean, each of these is a very skilled performance, and I don't think the skills from any one of those performances would transfer to any of the other ones. And yet somehow they are all recognizable in the large cultural umbrella that we call the guitar. So anyway, we undertook a kind of design exercise to try to figure out a little bit more about what's going on. And we built 4 simplified digital guitars in 4 different flavors. We built 2 different instruments that had, in place of the usual 6 strings, that had a touch sensor, a capacitive touch sensor that you would slide up and down to strum the strings. Whereas the other 2 instruments had little short lengths of string that you could literally strum or pluck. Now, we also had a variation in the shape, physical form of the instrument, where 2 of them had a guitar-like body, and the other 2 were in sort of smaller tabletop forms, which didn't explicitly resemble the guitar or any other familiar instrument. And I'll give you a little video of what these 4 instruments looked and sounded like. Right. So the activity was, amongst other things, to accompany that very tune that you heard. And as a sort of side note, that is a folk melody that was composed by an AI. That is Bob Sturm's Folk RNN, which has generated a fiddle tune of sorts that the participants were asked to accompany with a very simplified notation system. We got 16 guitarists, and we got 16 people who identified as non-musicians. And we each participant got one pair of instruments, which we called either the congruent pair, which was basically the strings on the guitar body and the touch sensor in a tabletop, or sometimes more interestingly, incongruent pair, where you had strings on the tabletop and the touch sensor on the guitar body. And we asked them a whole bunch of questions, like, which instrument is the most similar to a guitar? The congruent pair, the answer was sort of obvious. The guitar body with strings was a lot more like a guitar than the other one. But there was a huge amount of disagreement with the incongruent pair in terms of whether strings or guitar body made it more guitar-like. We asked people about which one you could imagine playing in a folk session. Again, a lot of disagreement, maybe tending more toward the strings. Which one allowed you to play in the most natural way? Again, nobody really agrees. What do we make of all this? Well, one thing that we make of it is that the kind of macro level form of the instruments and the micro level interaction are maybe not even as separable as we might have thought going in. You get comments from people like, this one feels like a weird approximation of the guitar because, the feeling of the strings is so familiar, but this one has strings, so it looks and sounds more like a guitar. Well, actually, the instruments were designed to sound the same, but these things are very much kind of tied together. And then, the touch guitar felt more cool because it felt more like an actual guitar and gave the impression of actually doing something similar to playing a guitar. Again, this sort of idea of guitaring as an activity. So there's a social function here as well as a technique. If you want to read more, it's in the papers. You can find this on the lab website. There was one other aspect of this study that we dug into, which was a fairly focal but important question around the richness of interaction. And the question was, does greater richness of control produce a better instrument? And so for the string instrument, we actually experimented with two different sound models. One of them was basically a kind of trigger model, which is what we used in the rest of the study. Basically, when a pluck was detected, it sort of triggered a sound at a constant volume and a constant timbre of that particular note. But the other model took the audio signal from the little piezo pickups that are on these strings, and it injected that signal straight into a mathematical model of a string, such that all of the nuance of your playing would be transferred into what came out of the other side. And for me as a string player, and as somebody who's spent a long time playing musical instruments, I sort of assumed that, of course, the greater the richness of control, the better the instrument is going to be. That is a thing that we strive for. It's even in my kind of earlier slides in this talk. It turned out the answer wasn't quite so simple as that. As expected, the guitarists universally preferred the richer of the two settings. And they said things like, everything that I did on the, on the simpler setting worked on the richer setting, but not vice versa. And that one of these really uses your knowledge of the guitar. On the other hand, the non-musicians were really split on which one they preferred, maybe even tending toward preferring the simpler one, because basically you didn't have to work as hard to generate the sounds, and you could produce something satisfying straight away. So there's clearly a relationship between what David Wessel calls control intimacy as a property of an instrument and the expertise of the players. So again, back to this question of sensorimotor skill. Now, just as a kind of a postscript on this, Strummy, as we've come to call the instrument, is going on to a long and varied lifetime in a number of different contexts. And there's a few papers that I could point you to if you want to learn more about this. So Jacob Harrison wrote a thesis around accessible digital musical instrument design, and Strummy features prominently in that, working with a group called Heart and Soul, which is works with musicians with learning disabilities. Evie Zayas has also done a number of papers and developed some instruments, or first replicating the Strummy as what we called a DMI apprenticeship, which was a kind of a way of training to build instruments in a kind of traditional apprentice workshop way, rather than sort of learning by the book. This has ultimately resulted in a new instrument, which is sort of strummy derived, but ultimately its own identity. And if I am correct, I think that's going to be shown at the demo session tonight. So stick around. And we also looked together at this idea of the research product, which is sort of like it's a concept coming from human-computer interaction, talking about you give somebody an artifact with a lot of sort of finish to it, not as a prototype of something that might hypothetically exist in the future, but something that is sort of self-contained and designed to be reacted to on its own terms. Not a commercial product, but not a prototype either. And this is a way of doing kind of research in the wild. So these are some papers you might have a look at. Okay. Back then to our three views of the musical instrument, our engineering view, our psychology view, and our ethnographic view. These are fundamentally tied up in one another. That the technology that we use to make instruments is itself a product of an ecology, whether that literal one, that musical one, or coming from somewhere else. It carries values with it. And the values of that technology carries ultimately shape the mediating role of the instrument. It changes how the performer thinks. And that in turn changes the kind of musical cultures that arise around an instrument. So these things are very much intertwined, and we have to think about the role of the technology. To put it in a very pithy way, Melvin Kranzberg writes, technology is neither good nor bad, nor is it neutral. In other words, every technology is going to carry values. What are those values? How do we learn about them? What do they mean for us? Well, one place that I turn to here is some of the teaching that I've done, and some of just my observation of things that have happened out there in the world of making interactive systems. One thing that you see is that there are a few kind of ideas that naturally occur to us when we start learning how to use some of this technology. And they occur over and over again, such that Tom Igoe, who is one of the creators of the processing language, even wrote a whole webpage about this. One of them is the theremin-like interaction. And here I don't necessarily mean literally waving your hands in the air above some electromagnetic antennas, but the idea of kind of simplified XY mappings. Pitch is this way, amplitude is that way. It's a very natural way to think about it when you're presented with these kind of technical systems. Another one is turning things into pianos. The Makey is a classic little board that lets you turn any object into a touch sensor, and people tend to do things like make pianos out of bits of fruit. And Emily Dolan writes about the kind of the way that the keyboard has sort of standardized our thinking about what music itself is, and this is why people tend to recreate pianos, even given an interface that could, in principle, do a lot of different things. Now, looking at the space of digital musical instrument research, one thing that I think sometimes emerges, which we have to be a bit cautious about, is what I'm going to call design by analysis. And it goes like this. It says, well, I want to make a digital instrument because I want to make music. Well, what does that mean? Well, probably when you're thinking about that, you're actually thinking about one particular style of music that you want to make, but maybe you're not even aware to yourself what that style is. But somehow it's been encoded in your thinking. Now, okay, so we want to make an instrument that's going to make music. Well, that's all well and good. Then we turn to, okay, what concepts do we have about music? In fact, what words do we have to describe concepts around music? So let's say that we were thinking about classical piano music. Well, okay, maybe what we're going to do is we're going to say, oh, we can think about what notes we play, what pitches, what velocities, what timing. Well, let's extend it in a sort of MIDI way and talk about different voices that might control different instrument sounds. And, maybe we want to even be a bit broader than that. Let's talk about what's the timbre of these things. Oh, maybe we can add some spatialization. Maybe we can add some effects. And what we end up with is a space that we then quantify. We turn it into a numerical dimension space. And the kind of implicit idea is that music making might consist of a navigation of this dimension space. I could describe a piece of music according to these dimensions. Could I therefore create one simply by navigating it? Well, okay. Then what we do is we turn to our toolbox and we open our toolbox. Oh, what do we have? Oh, we've got some sensors. We've got a force sensing resistor and some buttons and some this and some that. And we've got some programming languages. We've got Max MSP or Pure Data or something, and those do certain things. And ultimately, what that system is going to do is it's going to give us a different set of numerical qualities or numerical quantities. And then our instrument design exercise becomes a translation exercise between one dimension space and another. And this, of course, is what we call mapping. Now, the question is, does this process ultimately get us to the same place that other forms of instrument design might do? Maybe or maybe not. And the issue here is that objects tell us things. Even something as simple as a force sensing resistor invites you to kind of put it on a desk and push on it. And the ways of writing code themselves also have ways that they shape our thinking. I wrote this paper together with Koray Tahiroglu in Finland, where we were kind of looking a little bit at different computer music languages. And I speculate, and this is only speculation, that every computer music language might have its own sound. And that's not because of the way that the DSP operations are implemented, but because they make the composers think in different ways. And so for the final little bit of this talk, I want to talk just briefly about some languages that are out there. Max MSP, a very well-established language, originally developed by Miller Puckett at IRCAM in the 80s, has gone on to a successful life with Cycling 74. And then Miller later on created Pure Data, or PD, which is an open source version of the same kind of concept. And Miller writes that the design of Max goes to great lengths to avoid imposing a stylistic bias on the musician's output. And that maybe it's okay to sound like a computer so long as a computer is not understood to imply any stylistic tendency. Is this really true? Does this work? Well, Giacomo Lepri and I set out to try to discover it. And we made a little compositional game where people had a very short period of time to make instruments with some sensors, with PD and with Bella. Rather than telling you about the details of the study, I'll play you some videos of some little instruments that were made, again, in very short time, with the constraint that they were to be made with exactly one sensor at a time. So very simple. Here we go. All right, I'll stop that there for the moment and just make some general observations. A lot of interesting things came out of this, but one thing that's interesting is kind of what didn't happen. So we have here of the instruments that were made, sound was produced only by these three sound sources: a sine wave oscillator, a non-anti-aliased sawtooth oscillator, and white noise. And some instruments would use multiple of these, but there was never any instrument using samples, nothing using wavetables, and no other sorts of sound sources. And that didn't have to be the case, according to the design exercise. We also saw the way that people used the controls. We saw that there was a potentiometer that was most often used as a frequency control. The force sensing resistor was used very often to control either pitch or amplitude. And when people were given a button, it was often used to trigger an event or to randomize as a randomizer for elements like frequency. And then, even though both pitch and amplitude are perceived logarithmically, the large majority of instruments use linear scaling between control data and sonic output. Now, okay, why is that interesting? Well, it's because we have participants from a wide variety of different musical backgrounds who listen to all sorts of different music, but we never see things like samples or quantizing pitches to scales, or rhythmic patterns, step sequencers, etc. And the question basically is, why not? And the obvious answer is because they had 10 minutes. Well, fine. I'm not proposing that any of these instruments were anybody's ideal musical vision. But the point is they reflect the things that PD does very easily. They reflect the things that Bella and these sensors do easily. And where we start oftentimes has a real profound effect on where we end. The technology is carrying values, and those values are carrying through into the instruments that we make. It's not just the technology itself, but also the fact that there's a kind of community and a way of learning these technologies, again, the culture around the technology, that determines the way that people use languages like Max. To kind of bring this to a point here, Georgina Bourne and Joe Snape wrote a really, really nice chapter about the use of Max in different contexts. And they made a kind of observation that the technology that makes it possible for artists to forge unusual musical practices also locates those practices within familiar and consolidated technical and aesthetic universes. In other words, it is possible, I suggest, that we can be sort of seduced by the words and the numbers that we can come up with about music and the things that the technology suggests to us about how to make music, and that these can ultimately take the place of our lived experience of making music. And we have to work very hard to avoid these kinds of traps. Again, not to suggest anything at all, kind of deficient or wrong with Max or PD or any other language, nor to suggest that anyone is sort of there's any kind of technological determinism in the music that people make. Just to say that this music making is ultimately a conversation with the technologies and the values of the people who created it. So, basically, to conclude, instrument design is really complicated, right? It's technical, it has to do with sensorimotor skill, it has to do with cultural contexts, and there's more questions than answers here. One thing for me, I'm about to start in on a 5-year project, which I call Rudiments, Reflective Understanding of Digital Instruments as Musical Entanglements. And this idea of entanglement is essentially the kind of inseparability of humans and things and culture, a whole theoretical background, which I won't get into at this moment. But I might just say that if we look at the technologies that are really changing our world today, things like embedded computing, artificial intelligence. There's a lot of work at Queen Mary and other places on how to apply these things to music, but I think we can say with confidence these things will be used for music, no matter what. Sensors, AI, they are being used for music. And instead, the real questions are going to be things like, by whom? For what ends? Reflecting what values? Essentially, in just the way that the music making that we have today reflects, 40, 50 years of technological history and influence, decisions that we're making here and now may have ramifications that go far out from our current moment. And so I think what I would call for is just a self-aware, a reflective perspective, and ultimately a lot of conversations about how the engineering of an instrument and the culture around instruments are tightly coupled to one another. So I think I'll end on that note. If you want to learn anything more about the work in the lab, you can find that at instrumentslab.org. And we might have a couple minutes for questions, and otherwise you can certainly reach me here. So thank you very much.
You can still hear me okay, right?
Mm-hmm. Yep.
All right. So we can take some questions for sure. Yes. I don't know.
I don't exactly. Can you hear me? Yes.
Yes.
So I had a question about time actually. What's your idea about time? Because I think you mentioned it a bit in the idea of how people then relate to the development of instruments through time. But I wanted to ask you if you could say a few words, because I was thinking you mentioned a lot about repertoire, for example, being important, and this is something that builds up through a lot of time, of course, for instruments like violin or piano, etc. And I think in some kind of way there is a lot of repertoire during the last 20th century, second half of the 20th century. There is a lot, but that maybe it's not been explored through new instruments. But at the same time, I know there is there was a person that was doing some new theremin work, for example, and it's a performer, and she basically created a new way to play the theremin a few years ago. And then she basically created like a new kind of school, and then there's people now learning to play the theremin through her. And I think it's like kind of interesting that it's like an instrument that was invented like 60, 70 years ago that is kind of seeing new life through time. And same for Maximus P, like there's a lot of it. So how do you think like this actually happens?
Yeah, no, that's it's a really interesting observation. In fact, I heard a couple weeks ago at the proms a theremin concerto, which might be that very performer, and it was because the piece was written in the early 2000s, I think, and yeah, it's an instrument invented in the 20s, but it's maybe seen a bit of a renaissance through people who are skilled practitioners who can teach it, who can develop repertoire. Another instrument that you see that way is the owned Martineau, which was developed around the same time in the early 20th century. And the kind of continued legacy of that instrument owes an awful lot in the first case to Olivier Messiaen, who wrote pieces for it in the mid 20th century, and those pieces have helped sustain a school of practice for the instrument, and that has kept it alive. More recently, you have artists like Johnny Greenwood who've taken up the instrument and have been a kind of advocate for it. So yeah, I mean, these things take time to develop, and so I guess what my message is here is that when you're making a new instrument, you don't have the luxury of being able to create all of those things from day one. I didn't for the magnetic resonator piano either. I mean, now there's there's like 30 or 40 pieces that have been written for the instrument, and but that took it took more than 10 years to get to that point, and that there's still a long time in the future to consider. So one thing that you can do if you can't do this right away to start with is ask maybe how can you borrow resources that are already there? Is there existing repertoire that can be transcribed? Is there a way that you can connect to experiences that people have? The fact that people could play the piano makes it a lot easier for them to learn to play the MRP rather than something completely new. It's an interesting conversation. I don't have a lot of answers, I would say. It's just, but maybe one other thing that I would say is that sometimes the time spent is not necessarily even just time of trying to disseminate out to more and more and more people. It's perfectly reasonable to make an instrument for your own practice and for nobody else's. And you have cases like Michel Weiswitz, who was at Stein for many years and helped develop and then played this instrument called the Hands, which was a kind of gestural controller. And after a few years of developing mappings and kind of iterating the instrument, he said, no, we're not going to change how the instrument behaves at all. The important part now is to learn to play it and to learn to make music with it in the current form. So there was a deliberate kind of fixing of its capabilities. So yeah, time is an incredibly important element, and unfortunately, it's one that we just kind of have to wait for sometimes.
Thank you. Great, thank you. Any other questions? Yes.
Can I?
Yes. Yeah.
Thank you. Hi, Andrew. Can you see me?
I can hear you. Yep.
Okay. So, well, I actually have like 1,000 questions because it was like a panning of several things, and it's amazing to kind of reflect in this as myself an instrument builder, trying to be, right? So I guess maybe the question is super simple, and I was actually thinking about this just when you were talking. It's like why do we need new instruments? Like it seems like this idea that we kind of need new sounds, like we are getting tired of the sound of the violin, or do we need like new things? Like why is that? Why is that need of looking for new things? Like kind of like it seems to me that it's also a lot of entanglement with kind of this consumption, right? Like we need a new product, right? So how would we differentiate that? Because it makes me like kind of reflect, like am I going the right way, right? The sounds are there, right? We can listen to music that is amazing, that is like for 1,000 years old. And so what are we looking at? It's super,
that's actually a really profound question, actually. And I mean, and it's one that you can get a lot in this space. Well, why are you doing this anyway? And what's wrong with all the instruments that we already have? you mentioned the commercial motivation, and that's absolutely real. And I have a paper together with Jacob and Fabio in the lab where we looked at instruments that were made on Kickstarter and Indiegogo and similar campaigns. And they're oftentimes the aim is, of course, explicitly commercial, which is totally fine. And they say anybody can make music with this instrument. It's so easy. You can make any sound you can imagine. And it's sort of like there's this sort of almost kind of made for TV marketing of like nobody could make music until we came in and solved it with this amazing technology. And as you might imagine, I take a bit of a skeptical view toward that, but it does ultimately, help sell products, and that's, that's fine. That's and lots of people do cool things with those instruments. I guess more generally, well, you could actually step back one level further and say, well, why do we even bother making music to begin with? Don't we have enough music? I mean, you think about the catalog of recorded music that we have now is like just orders of magnitude longer than any individual could listen to in their entire lifetimes if they started the moment they were born until the moment that they died. So why do we need more music? We should have enough music. And I think maybe the thing is just to remember, music is an activity. It's not an object. It's a thing that we do. It's a thing we have to do. It's a thing that is a fundamental part of being human. And that's why I find it so fascinating when, basically archaeologists will uncover these bone flutes from 40,000 years ago. And you realize, what we're doing with embedded computing and AI and in a sense, it's the same thing that they were doing back then. It's that they took the technology that they had at the time and they said, how can I use this to express myself creatively? So why do you make an instrument? I think, well, it's because you have something that you want to say with that instrument. And it could be that you want to say it through your own performance, or it could be, as when it was in my case with the MRP, that you want to engage with other performers and, ultimately, maybe build a community around it. There doesn't have to be a kind of a goal-directed, progress-oriented narrative to any of this stuff, just like there isn't and probably shouldn't be with music itself. But I think at the same time, it's also good to remember that music can also be a vehicle for a lot of cultural and political values, and it can bounce around the world in surprising ways with effects that go well beyond the musical domain. And you can see that in terms of how digital audio workstations have shaped musics in other cultures who were not responsible for creating that kind of technology. And so maybe just a wider perspective is useful as well about what happens when I let this thing out of the lab. I doesn't answer the question, but maybe that's because the question is unanswerable, but it's a fantastic one to ask.
Yeah, thank you so much.
Other questions? Yeah. Andrew, great talk. First of all, I was wondering when we talk about the piano, I guess the piano now is not what the piano was 500 years ago. And if you had to make a prediction for what happens in 500 years, do you think that we will still talk about the piano, it will just have a very different form, or do you predict that it will be just vastly different instruments that you can't imagine right now? So do you think it will be more of a continue our current tradition and just enhance it more and more until it becomes something else, or that it will reach a point where we will create vastly different instruments that we can't even imagine?
I think it's more of an and than an or, really. I mean, I think that you will still see. I can't imagine that the piano will disappear from collective memory, short of some sort of catastrophic global event. But no, I register no predictions on that front. No, but I think we can also be absolutely assured that the instruments 500 years from now, or even 50 years from now, are going to be of a form that we can't anticipate at the moment. I mean, I think what you see, 500 years ago now, the piano wasn't the piano. I guess, you had the organ, of course, and then you had the clavichord and the harpsichord, and there's a long evolution for the piano to reach where it is today. The evolution is oftentimes not linear, though, right? The piano reached a state of sort of maturity in the late 19th century, and the design of the acoustic piano has largely stabilized since that point, notwithstanding various kinds of, kind of experimental extensions like my own, or, some other reinventions of the instrument. But in a way, you see that with music too. I mean, there are styles of music, not only classical, but certain genres of jazz and rock and such that were initially a popular music, a kind of musical vernacular, and then kind of coalesce into a certain art music tradition that is carried on and developed by generations of practitioners, which are very consciously respectful of the history of that music, rather than it having a kind of more functional role in present day society. And I think you could probably say the same thing about instruments, that there are some that are going to be kind of from the here and now, and maybe interest will wane when interest in that kind of music wanes. There will be others that are maintained very meticulously because of the cultural significance that they have. And then meanwhile, well, what's going to happen in 50 years with instruments depends on what kind of technology we have in 50 years, because we can be absolutely assured that any technology that's being used for any other purpose, somebody will make creative use of it. And what does that look like? Well, I guess we just have to wait around and find out.
Thank you, Andrew. And then a closing question, I think very related to what was last discussed. Yes. Sebastian just asked. So, and how does haptics come into all that? I feel I kind of have to ask this question given the context. For instance, you developed the MRP, being a pianist yourself. Actually, no, but you play the viola, so you play actually an instrument that has a very strong haptic feedback. A very well-documented audio haptic interaction for the musician. How do you use that in your research? How does this translate in like what's the place of these things, let's say, in rudiments and in moving forward?
It's actually incredibly important, and I didn't sort of explicitly talk about any of the haptically oriented research that we've done in the lab, but we have explored a number of things around both active tactile feedback, especially vibrotactile feedback, which I think is very important, and also just the kind of passive haptics of interacting with physical objects, which I think is in some ways maybe underrated as a resource for design. You don't have to have electromagnetic actuators pinging you with vibrations in order for haptics to be extremely important. On the MRP, just to take one example, the feeling of the keys, the weight of the keys, and the way they respond, and even the ways that you feel the vibrations of the instrument back through the keyboard are, I think, really important to getting a sense of how the instrument is behaving. And it's ultimately, if you want to have this effect that you and the instrument are entangled, that the instrument is an extension of you, or you're an extension of the instrument, maybe, then you need to have a way of kind of just tacitly understanding what's going on. And haptics is at least as important as sound to that. And so it's maybe this is my background as a string player is showing through in the sense that I'm very kind of preoccupied with micro level interactions, things that happen on kind of millimeter or less scales that you feel and hear, and that kind of happen in the here and now with a lot of detail. I think there's a lot you can do with that without actually explicitly having to add any actuators at all. But maybe the thing is just to be able to control something with a finer and finer level of detail if you want to, and to be able to have some notion of kind of where you are in the space while you're doing that. And that can be a combination of the sonic and the haptic means. I also haven't talked about anything about visual feedback, and I actually, for me, that's of secondary importance. One thing is just that the visual system's quite slow compared to either the auditory system or our tactile channels. But yeah, I could I could suggest some further papers to read around this, and the work around Strummy and the different levels of detail on the sound models, I think, has haptic implications as well as audio ones. So yeah.
Great, thank you. So if there are no other questions, thank you very much again, Andrew, for joining us.
Great. Well, thanks very much. And I'm sorry I couldn't join you there in person, but thanks for making this happen remotely. And yeah, do stick around for the concert. Hope everyone there. It looks to be a really exciting event. And yeah, enjoy the rest of the conference.
Great. Thank you.
Good. All right. Bye.
Bye-bye. Bye, Andrew. Right. Program. Downstairs in the ground floor of this building, where our reception is, our welcome